All right, so we're picking up on slide 13 of the second PowerPoint of chapter 14. Slide 13, PowerPoint 14, part 2. Okay, we're talking about energy profiles, sometimes called reaction profiles or reaction diagrams. But essentially what we're doing is we're trying to represent the energetics of a reaction in a graphical form, where on the x-axis, we label it as progress of the reaction, but essentially we're saying we start out on the left side with the reactants. As we move to the right, we're converting the reactants into products. If the reactant energy is higher than the product energy, that would be an indication that this is an exothermic reaction, because if the reactants contain more energy, which is, when we started this diagram, we put the reactants at an arbitrary level, but then if we know the product energy is lower, that means that we must have released energy from inside the system to the surroundings. If we release energy to the outside, then that means that our energy drops. That's the definition of an exothermic reaction. Now, there's other important information here. My reactant molecules have some initial energy. In order to convert into products, they have to crash into each other with enough energy. That's the reactant molecules have to crash into each other with enough energy to break a bond. If they break a bond, that creates unstable intermediates that can then be converted into products. If the reactant molecules collide with less energy than enough to get over the hump, then the reaction doesn't happen. We have to have at least this much energy involved in the collision in order to get to the other side. Okay? And then just important things, we can actually label, if we know the value of the activation energy, we need to make sure that mathematically that number represents on the y-axis the energy level. And then also from the beginning to the end, we can put that would be the value of delta H, the enthalpy of reaction. So if we look at three different reaction energy profiles, we'd say the first one, from my starting point, if it goes up that high on the scale that's given, that's 15 kilojoules per mole. From the starting point to the top of the hill, that's the activation energy. And then from the beginning to the end, it goes down by 10 kilojoules per mole. So that's a exothermic reaction. Delta H would equal negative 10 kilojoules per mole. Okay? The next one, very similar, but it's got a higher activation energy, and then a larger delta H value, more negative. Okay? And then the last one is going to be endothermic, where my energy, my products, is actually a little higher than my reactants were. So, a few questions. Which reaction is endothermic? Well, again, endothermic is going to be the one where my product is higher than my reactants, so that's graph number 3 right here. Which ones are exothermic? Be the other two. Okay, so here we get into new information. Which reaction would be the fastest? Okay, now the fastest reaction is going to be the reaction where the most molecules are going to collide with enough energy to overcome the activation energy. Now, which one would that be? Well, if we assume all these are at the same temperature, the one that has the smallest obstacle in the way is going to go the fastest. Now, the obstacle to the reaction is the activation energy. So if I have an activation energy of 15 kilojoules per mole, 25 kilojoules per mole, or 20 kilojoules per mole, those are the three activation energies. The smallest one, which is graph number 1, is going to be the one that goes the fastest. Which one's the slowest? That would be the one with the biggest obstacle, the biggest hurdle that it has to get over. That's going to be graph 2. It has the largest activation energy. That's going to make it be the slowest reaction. Now, something we haven't talked about. Some reactions will, normally reactions go from left to right, but we're going to occasionally have cases, especially in the next chapter, where reactions can go backwards. Okay? We call that a reverse reaction. So which one of these reverse reactions would be the slowest? That's going to be the one, if I look at now I'm starting on the right and I'm going to the left, I can recalculate what my new activation energies are. So from here to the top of the hill, that's going to be 10 plus 15. The activation energy going that way is going to be 25. This one, 15 plus 25, the activation energy here is 40. And then this one, I'm up 5, I'm up 20, that's going to be 15 on that one. So the one going backwards that has the highest activation energy would be the middle one. So the reverse reaction of the middle reaction would be the slowest. All right, now, things that we need to be able to label. If we draw a reaction energy diagram or a reaction profile, we should be able to label all of these parts. Okay, we should be able to label on the left side we have the reactants, on the right side we have the products. When we go up to the top, we're going to have the activation energy, which is E sub A. When we are converting the reactants to products, at the point where, at the highest point, that's where I'm breaking bonds. I'm kind of making really unstable species at that point where they don't have as many bonds as they would like to have. They don't exist for very long because if they're really unstable, it's going to try to shift from the reactant into whatever the product is as quickly as possible. But in between, we have something that's called a transition state. So at the top of the hill, at the top of the activation energy, we're going to have the transition state, which some books are going to refer to as the activated complex. Okay? The transition state or the activated complex is an extremely unstable species that exists at the top of a hill between the reactant side and the product side. All right? And then if we're doing a multi-step process, after each step, sometimes we're going to form a molecule or ion that's a little bit stable, but it's not really one of my final products. I'm going to form it, I'm going to have it for a little while, but then it gets used in a later step. That's going to be called an intermediate. All right? And then finally, we're going to have catalyst, which a catalyst is something that's present in the beginning of the reaction. It gets used or it helps the reaction occur, but then when we get to the end, it needs to still be there. Okay? Now, sometimes the catalyst will be used or changed into another form during the process, but by the time you get to the end, we have to have it back again. Okay? Again, we'll see all these things as we go, but just make sure that when you draw a reaction profile, we're going to expect all these things to be labeled on the graph. And then we should be able to look at a graph and easily tell, is the reaction endothermic or exothermic? And we can look at the overall reaction from beginning to end, or if we have multiple steps involved, we should be able to look at each step and determine, is step 1 endothermic or exothermic? And then step 2, is it endothermic or exothermic? And so on. Okay? And then, so that's endothermic or exothermic on each step and on the reaction, and each one of those is going to be a delta H value. So you're going to have intermediate delta H's, and then you're going to have the overall delta H at the end. Again, we'll see that in a graph in just a minute. So, a multi-step reaction profile, we will recognize this based on the number of humps we have in the middle. If we have a one-step reaction, then from the beginning to the end, there'll just be one hump in the middle. That is a single-step reaction. Okay? Now, if we have a multi-step reaction, then basically each hump in the graph is going to represent one step. All right? So, in this diagram, I start with my reactants. I'm going to go through one step of the reaction. It's going to take me over the first hump. And when I finish the first step, I'm going to form some molecule or ion that's called an intermediate. It'll be there for a little while. It's kind of stable, but then it's not one of my final products. So I need to do another step. I have to continue the reaction, do step 2, and go over another activation energy before I can get to my products. So this diagram is a 2-step process because it has 2 humps. At the top of each hill, I would have a transition state, which is something that exists for a moment that's very unstable. In between the steps, I'm going to have an intermediate or multiple intermediates. It could depend on the reaction as to how many intermediates there are. But that's something that's a little more stable. I can see by the drop in energy, anything that's low energy is more stable than things that are high energy. Okay? So that's why my transition states, I know that they're unstable because they're so high energy. The intermediate is relatively stable compared to what I had before and after. And then when I get to my products, this reaction, since the reactants are low energy, the products are high energy, I could say that this is a overall endothermic process. Okay, now I can also break it down step by step. The first step is endothermic, because I go from here to here. That's definitely an increase in energy. But then the second step, I go from here to here. That is actually an exothermic step. Okay? And then I could go one step further. Of these two steps, which one's going to be the slower step and which one's going to be the faster step? Well, if you remember our previous slide, we said that a slow step will have a larger activation energy. So the first step, I have to get from here all the way to the top of the hill. That's a huge barrier that I have to overcome. So in this reaction, the first step will be very slow. But then once I get past the first step, the second step is actually a very small barrier here. The activation energy for this one, from here to there, that's small. So the second step will be fast. Okay? That's going to be very important as we move on to the next section. So the precise sequence of bond breaking and bond making that occurs in a reaction is called the reaction mechanism. Essentially what that means is if we want to understand how a reaction occurs, if it happens in multiple steps, we need to figure out what's going on in each step. Okay? Now an example that everybody's heard of, at some point you've probably taken a biology class, and in that biology class you learn about like the Krebs cycle, where and again, I'm not a biologist, so don't hold me accountable for this. But when we eat sugar and our body breaks it down to CO2 and water and produces ATP, during that process, all the things that happen, they don't happen in one step. There's probably 25 or 30 different little chemical reactions that occur in that overall process. If we understand what every step of that process is, that's what a mechanism is. A reaction mechanism, it lays out step by step how a long process occurs. Okay? Now, we are examining like the molecules, we're examining to see with each step that happens, okay, in one step I might break a bond. And in the next step I might form a bond. And then a step after that I might break another bond, right? So we're looking at the molecular level to see what's going on with all the bonds in the atoms and which ones are connecting and which ones are being broken apart. If we write all that out, that's what a reaction mechanism. If we want to really understand how chemistry works, how reactions happen, why do some reactions go fast and other reactions go slow, we need to look at reaction mechanisms. That's the only way that we're going to understand the kinetics, like why things go fast, why they go slow. So now this can apply. Most reactions are actually not single step. If we look out at all the reactions that we observe in chemistry, most of them happen as a series of steps. They don't happen all at once. So we need to break it down. Each step, if it's a singular event, we call that an elementary step, meaning only one thing's happening, or if it's two things, they're happening simultaneously. Okay? So very simple, like if one molecular event occurs, that's an elementary step. We can write a reaction to represent that step. If we can write out all the steps, we should be able to apply Hess's law and add them all back up to get the overall reactions occurring. Again, cellular respiration, we know it's glucose plus 6 oxygens yields 6 waters and 6 CO2s. We know that that's the balanced overall reaction. If we add together all the molecules and all the steps along the way, we should be able to simplify it back down to the overall reaction that we started with. An example, one that we've seen from 1211. If I mix together sodium carbonate with hydrochloric acid, I know that what will happen initially, that's a double displacement reaction. So I swap partners, the sodium goes with chloride, the hydrogen goes with carbonate. So when I swap partners, these are my products. Okay? But if you remember from 1211, if we form carbonic acid in solution, that's an unstable compound. And what's going to happen, right after I form carbonic acid, I know it's going to split apart and form H2O, and then CO2 bubbles are going to form. So when I mix hydrochloric acid and sodium carbonate, it's double displacement, but then there's a decomposition that occurs, and what I'll observe is it's going to fizz and give out bubbles. Okay? So I can write this reaction as 2 steps, but then for my overall reaction, I should be able to add these together. So I add together all my reactants, I add together all my products, I cancel out anything that appears on both sides, and then that's going to give me my overall reaction, which is Na2CO3 plus HCl yields H2O and CO2. This is my overall reaction that occurs. Okay, so we have several steps of a mechanism that can occur. Some mechanisms will be 2 steps, some will be 3 steps. You even have some in biology that might be 30, 40, 50 steps. Okay, however many steps you have, when we draw out the diagram, every step is going to have its own hump on the diagram, which means every step has its own activation energy, which is a barrier to the reaction occurring. We have to get over that barrier before we can do the next step. And if we have an activation energy, that also means that we have a rate constant. Every step has its own rate constant. Now, when we look at these, when we have an elementary step, this is a new thing, when we have an elementary step, the order of if we write out the rate law, the order that we put on each reactant for a given step will actually match up with the coefficient of the reactant in that equation. Okay? So if I write out the reaction that applies to a step, like step 1, write out the reaction. Whatever the coefficients are on the reactants, those are going to match up with the exponents of my rate law. Okay? Now, we didn't tell you this before in the beginning of chapter 14 because, remember, most reactions, we don't know when we look at a reaction if it's going to be a single-step reaction or a multi-step reaction. Okay? If a reaction is going to be a multi-step process, we can't apply this statement unless we're looking at the individual steps of the reaction. You can't use the coefficients from the overall reaction. You have to be looking at the mechanism. You have to know that what you're looking at is a single step. And if that's true, then we can take the coefficients and make them the exponents in the rate law. Okay? Now we call that whatever the coefficients are on the reaction side of a step, if we add those coefficients up, that's called the molecularity of the reaction. Again, the next slide will clear that up a little bit. And then when we talk about an overall reaction, how fast is it going to be? It's going to be based on the slowest step. Imagine I pick 5 people and I tell them they have to run a race, they have to run a mile, but they have to hold hands the whole way. The person who's going to determine how quickly they can run the race is going to be the slowest one of the 5. Okay? 5 people running together, they can't go any faster than the slowest person in the group. Okay? So even if one person wants to go really fast, they can't because they're tied to the other 4. Okay? Well, in a reaction mechanism, when you have all these steps, if there's one step that's really slow, it's going to hold the whole process up. You can't get through the mechanism without going through that slow step. So the slow step is going to be the one that holds everything back. Again, example, if I were driving into Atlanta and, I'm hopping on 985 at, 6 in the morning and I'm driving in, 985, the traffic's usually not that bad in the morning. Even when it gets down and merges with 85, it's not that bad. But when we get down to Spaghetti Junction, right as we're getting to 285 and getting into Atlanta, that's where all the cars come together and you end up with a bad traffic jam. So if I'm going to figure out how long is it going to take me to drive into Atlanta, I'm going to pull up my map, I'm going to look at Spaghetti Junction and see how slow the traffic is there and know that that's probably my limiting factor. That's what's going to keep me from getting to work on time. Okay? The slowest part of the process controls the speed of the whole process. All right. That's long enough on this video. I'll pick up this slide on the next one.